So now you must be understanding this time quantum value decides number of context switches and the response time. Okay, when the time quantum value reduces, then what happens? Your number of context switches increases and your response time also gets decreased. Why so? So let's say your time quantum value is 1 second. So what will happen? Let's say P1 is getting executed. After 1 second, P2 will get scheduled. After one more second, P3 will get scheduled. Then after 1 second, P4 will get scheduled. So as a result, every second there will be a context switch. Alright. So let's take one window of 10 seconds. So what will happen in this 10-second window? You will end up seeing 10 different processes. Okay. So it says all the processes are getting chance very early. So as a result, this response time is also low. So when this time quantum value is much more higher, then what happens? Let's say P1 is getting scheduled here. Let's say your time quantum value is 5 seconds. Okay. So for the next 5 seconds, your P1 continues. Then P2 comes and it also continues for the 5 seconds. Okay. So you can see every 5 seconds there will be a context switch. So in this case, every 1 second there was a context switch, and here every 5 seconds there is a context switch. So as a result, here number of context switches are much lesser. So let's take a 10-second window here also. So in this example, when this time quantum value was 1 second, in a 10-second window, you ended up seeing 10 different processes. Okay. But here, when this time quantum value is 5 seconds, okay, then this in this 10-second window, you will end up seeing only 2 processes. Okay. So in a particular window, very less number of processes are getting chance. Okay. So as a result, so all these processes are getting chance, but in delayed way, not getting chance very fast. So as a result, this response time is also high. So the issue is, let's say you are typing DOG in your keyboard. So ideally, whenever you are pressing the key D, you are expecting that you will see D on the screen. So the moment you are pressing O, you will expect that O will be coming up on the screen. So whenever you are pressing G, you will expect that G will be coming up on the screen as soon as possible. So if this response time is much more higher, it may happen that you have pressed D, then O, then G, then suddenly D has come. Then after a few seconds, O has come, something like this. So this experience will be very much laggy. So this is something you may face when this response time is much more higher. Okay. So when this time quantum value is too high, then this becomes first come first serve, nothing else. Okay. So choosing the right time quantum value is the main challenge in this round robin algorithm. All right. So now let's solve this example. Okay. I have just copied and pasted the same question. Like these are the processes, these are the arrival time, these are the bus times. I have copied as it is. Okay. So let's see the Gantt chart. Okay. So at time t equal to 0, your Gantt chart is getting started. Okay. So at time t equal to 0, do you have any processes? The answer is no, you don't have any process. So time t equal to 0 to time t equal to 1, your CPU will be idle. Okay. At time t equal to 1, so whenever you are trying to schedule one more process, what you will have to do is, first thing is you'll have to update your queue. So let's update the queue. As of now, your queue is empty. At time t equal to 1, we are standing. So at time t equal to 1, you have only these two processes, 1 and 2. So process 1 and process 2. These two are in the queue as of now. Okay, fine. So your queue is updated. Now what to do? Take the first process from the queue and schedule it. Let's say P1 is scheduled here and P1 is popped out from this place. Okay. So what was the time quantum value? Time quantum value was 2 units or 2 seconds. Okay. So but its burst time is 5 unit of time. So P1 will be scheduled for how much time? For 2 unit of time. Okay. So 1 plus 2 becomes 3. Now this 5 will be becoming 5 minus 2, that is 3. You are supposed to find what is the next process you will be scheduling here. Before you find the next process, you will have to update your queue. You are standing at time t equal to 3. Now let's see what are the processes that have come by time t equal to 3. You already had P1, P2. Okay, by time t equal to 3, you have this process P3 and P4 both. So P3 and P4 both. Now the question is P1 completely executed? Answer is no, because it has 3 more unit of burst time. Now you will have to push this P1 again in the queue. Okay. Now remove the process that is sitting in the first position of the queue, that is P2, and schedule this P2 here. Okay. Now P2 will be executed for 2 more unit of time. Okay. So 3 plus 2 becomes 5. Now this 4 will be becoming, this burst time of P2 will be becoming 2. Why so? Because 4 minus 2 is equal to 2. Okay. So now before scheduling the next process, you will have to update your queue again. So the next question is, by time t equal to 5, do you have any new process? If you see at time t equal to 4, process 5 has come. So that means by the time you have reached time t equal to 5, you have processed P5 also in the queue. Now the next question is P2 completed? Answer is no. As a result, you have to push P2 again. So now again schedule this P3. That is the first process in the queue. Schedule P3 here. Okay. So P3 will get executed for 2 more unit of time. So 5 plus 2 is equal to 7. This 2 will be becoming 0. Okay. So before scheduling the next process, you will have to update the queue. Okay. So by the time t equal to 7, do you have any new process? Answer is no. So is P3 completely done with the execution? Answer is yes. So you don't have to push any new process in the queue. So now see the next process sitting in the first of the queue, that is P4, and pop this from the queue and schedule this P4 here. For how much time? For 2 unit of time. But P4 is expecting only 1 unit of burst time. So what is the point of giving 2 unit of time? There is no point. Just give 1 unit of time and get done with the process P4. 7 plus 1, that is 8. 1 will become 0. So now you'll have to find what is the next process you will be scheduling here. But before that, what you will have to do? Before that, you will have to update your queue. Alright. So by the time t equal to 8, do you have any new process? Answer is no. Are you done with the current process, that is P4? Answer is yes. So you don't have to push any new process here. Okay. So now your queue updation is done. So see which process is sitting at the first of the queue as of now, which is P1. Schedule P1 here. Okay. So what is the burst time P1 is expecting as of now? That is 3 units. Okay. But your time quantum is 2 units. So as a result, you will be allocating only 2 units of time. So 8 plus 2 means 10. Alright. So this 3 will be becoming how much? 3 minus 2 is 1. Now the next question is, before you schedule the next process, you will have to update your queue. So by the time t equal to 10, do you have any new process? Answer is no. Are you done with this process P1? Answer is no, because P1 is expecting 1 more unit of time. As a result, you have to push P1 in the queue. Okay. So before you schedule this P1 here, you had to pop this P1 from here. Okay. So at time t equal to 10, you found no other new process and your P1 was expecting 1 more unit of time. That is why you had to push this P1 again in the queue. Okay. Now at time t equal to 10, you have updated your queue. Okay. Now see which process is sitting at the first of the queue, that is P5. Pop this P5 from here, schedule this P5 here. So what is the time P5 is expecting? That is 3 unit of time. So you will have to schedule it for 2 more unit of time because time quantum is 2. So 10 plus 2 becomes 12. Okay. So now this burst time of P5 will becoming 3 minus 2, that is 1. Okay. So now before you schedule the next process, you will have to update your queue. By the time t equal to 12, do you have any new process? Answer is no. So next question is your P5 completely done with the execution? Answer is no, because P5 is expecting 1 more unit of burst time. So what you will have to do? You will have to push P5 again here. So now you are done with the updation of the queue. So now your queue is updated. Okay. So now let's see which process is waiting at the beginning of the queue. Okay. So that is process P2. What you will have to do? You will have to remove this process P2. You will have to schedule process P2 here. So what is the burst time P2 is expecting? That is 2 unit. What is the time quantum value we have? That is also 2 unit. So pick P2 and run it for next 2 more units. So 12 plus 2, that is 14. So P2 will be becoming how much? 0. So now before you schedule the next process, you will have to update your queue. By the time t equal to 14, do you have any new process? Answer is no. Is your P2 done with execution? Answer is yes. So you don't have to push P2 again in the queue. Now let's see which process is waiting at the beginning of the queue. That is process P1. Remove this process P1, schedule this process P1 here. So process P1 is expecting 1 more unit of burst time. So 14 plus 1, that is 15. After 15, process number 1 is gone. So now you will have to schedule the next process. So before you do that, you will have to update your queue. So by the time t equal to 15, do you have any new process? Answer is no. And one more question. Are you completely done with the execution of process P1? Answer is yes. So you don't have to push P1 again in the queue. So now your queue is updated. Now let's see which process is waiting at the beginning of the queue, that is process P5. Pop this process P5 from here, schedule this process P5 here. So how much time process P5 is expecting more? That is 1 unit of time. So 15 plus 1, that becomes 16. Alright. So now you are done with creating the Gantt chart. So now let me fill the other part. let's say completion time, then comes maybe turnaround time, then comes your waiting time, then comes your response time. Okay, what I have told you, the trick is while filling the completion time, you will have to come from this side. Okay, so process P5 is done at time t equal to 16. Process P1 is done at time t equal to 15. Sorry, this is process P1. Okay, so P1 is done at time t equal to 15. So now come like this, process P2. P2 is finished at time t equal to 14. So now again keep on coming like this, P2 is done, then P5, P5 is also done, then P1, P1 is also done, then comes P4. When P4 is getting finished at time t equal to 8. Okay, so this is the completion time of P4 is 8, P4 is done. Next you go with P3. So when P3 is getting finished at time t equal to 7. So now what you will have to do, you will have to calculate the turnaround time. So we all know turnaround time is the difference between completion time minus arrival time. So 15 minus 1, that is how much? 14. 14 minus 1, that is 13. 7 minus 2, how much? 5. Okay. 8 minus 3, that is 5. 16 minus 4, that is 12. So now here we go with the waiting time. So what is waiting time? We all know that turnaround time equal to wait time plus burst time. So wait time becomes turnaround time minus burst time. So this is the turnaround time and this is the burst time. You'll have to refer the original burst time. So 14 minus 5, 5 was the original burst time. So 14 minus 5 becomes 9. 13 minus 4, that becomes 9. 5 minus 2, that becomes 3. 5 minus 1, that becomes 4. 12 minus 3, that becomes 9. Okay, now let's calculate the response time. What is the response time? So while calculating the response time, the trick is you will have to come from this side. All right, what is the first time when this process P1 was scheduled? That is time t equal to 1. When this process P1 has arrived, that is also time t equal to 1. So what is the difference between 1 and 1? That is 0. So now comes process P2. Okay, so process P2 is scheduled for the first time at time t equal to 3. When it has arrived, that is time t equal to 1. So 3 minus 1 is how much? That is 2. Then process P3, when it is scheduled for the first time, that is time t equal to 5. When it has arrived, time t equal to 2. So 5 minus 2 becomes 3. So then process P4. P4 is scheduled at time t equal to 7. I mean P4 is scheduled for the first time at time t equal to 7. Okay. And when P4 has arrived, that is time t equal to 3. So 7 minus 3 becomes 4. Again, if you keep on going like this, P1 we have already scheduled. Now comes P5. Okay. When P5 is scheduled for the first time at time t equal to 10. When it has arrived, time t equal to 4. So 10 minus 4 becomes 6. So as a result, you have finished the entire table. So now let's move to the next part and the last part. So first thing is, what is schedule length? Schedule length is maximum completion time across all the processes minus minimum arrival time across all the processes. Okay. So what is the maximum completion time across all the processes? That is 16 minus minimum arrival time across all the processes. Okay. How much is that? That is 1. This one. All right. So 16 minus 1, that becomes how much? 15. So throughput is number of processes divided by schedule length. So what is the number of processes? That is 5. And what is the schedule length? That is 15. All right. So now let's calculate the efficiency of the CPU. So efficiency of the CPU is schedule length, that is L, minus wasted time, wasted as in either in context switch time or the time your CPU remains idle. Okay. So schedule length minus wasted time by the CPU divided by schedule length. So if you see this Gantt chart, this 0 to 1, this part is the idle time. But in this case, you will not be considering it as wasted time. Alright. Why so? The reason is you will have to find the total wasted time after the first process's arrival. Okay. So when your first process is arriving at time t equal to 1. So while calculating efficiency and while finding this wasted time, you will have to find the total wasted time after time t equal to 1. And why 1? Because 1 is the minimum arrival time across all the processes. Alright. So after 1, if you see the Gantt chart, there is no wasted time. So what will be this? L minus 0 divided by L, because wasted time is 0 unit. Okay. That means 100% is the efficiency. Even though this is not very much practical, because here we have not considered any context switch time and we have not considered any IO time. Alright. So that is why the efficiency has turned out to be 100%. So now let's calculate total number of context switches. So how to calculate total number of context switches from this Gantt chart? What I have told you in the previous videos, just calculate the number of cells like this. 1, then this is second, then this is third, fourth, fifth, sixth, seventh, 8th, 9th. All right. So how many context switches are there? There are total 9 number of context switches. All right.